12.1, Triangle Proportionality Theorem, Geometry. Essential question: when a line is parallel to one side of a triangle intersects the other two sides, how does it divide those sides? So if basically, and the funny thing about geometry is you always need a pretty picture. So let's say you got a triangle, and then all of a sudden you have a smaller triangle embedded inside the bigger one, okay? And basically, when a line is parallel, so this line is parallel to this line, okay? How does it divide those sides? So last module we talked about proportionality, and guess what? We're going to talk about it again. So your answer is the line cuts two sides of a triangle into segments. So therefore you have this segment here, this segment here, this segment here, this segment here, okay? And the ratios between the two segments of each side are equal, okay? And notice how they say ratios. So we're still dealing with proportionality, okay? So here's a prettier picture with the theorem. Triangle proportionality theorem. So your theorem states if a line parallel to a side of a triangle intersects the other two sides, then it divides both those sides proportionally. So basically you have a parallel line cutting through, it intersects two sides of your triangle, and it divides those sides proportionally. So what we mean by that is, if you notice a smaller piece AE, right, it's going to be proportional to AF, okay? And the way that the book sets it up in their proportionality statement, like in your test, where you had to list like 6 different proportionalities, okay, AE is going to be proportional to AF, okay? Normally you put the, well, a nice habit is putting AE over AF, but the book likes to do it where AE is equal to AF, and then you talk about the longer sides at in the denominators. So AE is proportional to AF, and EB is going to be proportional to FC. And that's how they set it up, okay? And basically you need to know, and they usually give you this idea, okay? Those two lines, they're parallel, okay? Therefore, that's what you can conclude, is that all those little segments are proportional. So let's look at some examples. Example 1, find the length of CY. So notice in your image that they go ahead and tell us that BC is parallel to XY. Awesome. So it kind of gives you like all right, just set it up. So they tell us that they're parallel. All right, CB and XY. Therefore, by the triangle proportionality theorem, you should be able to say that, and we're looking for CY, that CY is proportional to BX, and that should equal the proportionality of AY to AX. Okay, so you should be able to do that. So here I am saying that CY is proportional to BX, like I previously stated, and that AY is proportional to AX. Okay, CY over BX equals AY over AX. Go ahead and substitute. Notice how I put CY on the top left of our proportionality. It's just because it's easier to solve for X or a missing piece when it's in the top left. You don't have to use the reciprocal rule, and it's just more algebra. So if you set it up right, you don't have to do as much math. So we're going to go ahead, get rid of that denominator of that 4. So you can cross multiply, or you could be a boss and just multiply both sides by 4. Because 4 times 1/4 will be just 1, and you just live with cy over 1, which is just cy. And then 4 times the 10 is 40, and then divide by the 9. You could leave your answer as an improper fraction. Just be aware of maybe perhaps getting decimal answers. Okay, that can happen too. But impropers like 40 over 9, I would accept it. Okay. Example 2 and 3. So I decided to be a pro and just do 2 on the same slide. So we're going to find DG. So let's see, if you're just looking at the image, you should be thinking, oh, okay, I got parallel lines given to me. That's nice in the picture, right? That's awesome. So therefore, by the triangle proportionality theorem, let's see, DG, the one we're looking for, should be proportional to CF. So I'm probably going to have DG over CF. And then the other two segments, it's going to be ED, and that guy should be proportional to CE. All right, so you should be thinking that way, visually. Then just write it. Okay, so DG is proportional to CF equals ED to proportional of EC. Since we're finding DG, we're going to go ahead and start substituting the values that we know. And you're going to cross multiply, or again, like a pro, you could just multiply both the left hand and right hand side by 24. And 24 times 40 is 960, and then divide by 32. And you'll get DG is 30. Epic. Now, example 3. Or number 6, because I apparently forgot to take out the 6. I'm assuming, well, first they tell us that these guys are parallel again, right? So that's good. So the triangle proportionality theorem should kick in. We're looking for Rn, and Rn is going to be proportional to QP, and MR should be proportional to MQ. So you should get a proportionality statement like this. Notice how Rn is in the top left because that's what I care about, and I don't really want to do more math than what the book would probably show you. Go ahead and substitute, like in example 2. You can multiply again instead of using the reciprocal. It's up to you, but sometimes it's just more efficient to think this way. So I'm going to multiply both the left hand and right hand side, and that's what gets me to my 50 over 8. And I believe in the book you can reduce 25 over 4, or in middle school and I think elementary they did 6 1/4 or 6.25 in your calculator. Okay, so those are 2 more examples. All right, so here leads to the converse of the triangle proportionality. Okay, so unlike the regular triangle proportionality, you're just going backwards with the statement. So instead of them telling you that 2 lines are parallel, they're just telling you right off the bat, okay, these segments, they're all proportional. So in the theorem, if the line divides 2 sides of the triangle proportionally, so they already tell you something like this, okay, then it's parallel to the third side. So they don't give you the whole parallel thing like they do on the previous examples right away. They just tell you that they're proportional. And then the problem will most likely be something like, prove that your 2 lines are parallel. Okay, that's like going the other way with it. So let's go ahead and see an example. All right, so notice how they didn't tell us that the lines are parallel, but we have to verify that they are. Well, for them to be parallel, the line segments have to be proportional. So if they're proportional, we have to, well, we need to be able to visually see this. So KM has to be proportional to that guy. Okay, has to. And then Jm has to be proportional to Jn. Okay, so how do we set this up? Well, we have to prove that they're proportional. So Jm, okay, is going to be proportional to Mk. Oh, okay, so it looks like the book decided to use a different proportionality. So let me erase this thought. Basically, they're saying that, and I would have done it differently, but I would have gotten the same proof, same answer. Basically, they're saying Jm is proportional to Mk. So Jm is proportional to Mk. Okay? Think of like a dilation. You're dilating out from J. They should be proportional, right? So that's what it's thinking. All right, it's like launching out. It's dilating by a center of dilation from J type deal. Okay, and then they say Jn is proportional to NL. Okay, so remember proportionality has to exist with dilations. Okay, so it's kind of like harking back from that old idea. All right, so let's substitute in our values. And then eventually you'll just get some number equaling the same number. Does 2 equal 2? Yeah, that true. That true. All right, true that. So, since they are proportional, you can say by the converse of triangle proportionality theorem, Mn is parallel to KL. Okay, and that's how you can prove it using proportionality and algebra. Which there's a couple problems that do that to you in the homework. And speaking of which, there's your homework. Good luck. If you have any questions, come see me.